So Joe, who will talk about immersive Earth science data visualization. So Joe, are you online?
Yes, I'm online. I'm bringing up my
Alrighty.
slides now. Are you seeing this okay?
Yep, you cross well.
All right, perfect. So my name is Joe Roberts. I am a member of the Science Data Visualization Group at JPL. I do a lot of work with Earth science data systems. So today I wanted to talk about immersive Earth science data visualization using a tool we built called SciVR. So a little bit about Earth science data. We have a lot of highly detailed 3D data of the Earth. So I'm talking about climate and weather models, radar, sounders, and other instruments from our fleet of satellites. We also have airborne terrestrial LiDAR, as well as in situ probes, so measurements on the ground, basically. And we all know about the possibilities of XR. So how about adapting this to geospatial data sets and use it in an immersive collaborative environment? So in particular, working with Earth scientists, how do we leverage this new technology? And I have a quote from one of our scientists here. So he was very interested in taking what appears to be a wishful dream and making it into an efficient implementation of virtual reality for science. So here are a couple of examples of 3D or science data. This is measurements of relative humidity from airs overlaid on a 3D globe, and underneath it you can actually see imagery. I think this is off the coast of Africa, so we're looking at Sahara dust that's actually blowing into the Atlantic Ocean. Here's another video from the NASA Goddard Science Data Visualization Studio. So this is an ocean circulation model called ECHO. I really like this one because you can see underneath the ocean and see the circulation happening beneath it. So seeing something like this in an immersive environment would be really, really cool. And here it zooms out to see several of our satellites orbiting the Earth. So SciVR, this is a fully immersive science data visualization application that was built specifically for Earth scientists. So this lets them explore their data in a room scale environment in real time, using all the great things about VR, the natural depth perception, tracked hand motions, and building in specialized tools. So being able to slice through volumetric data, scale the data sets, and query data values. We built this originally in Unity for the Vive and Vive Pro. So it's really intended for high-end computing and larger data sets. It was developed to help scientists better understand their data and shorten the feedback loop of discovery. So making really fast, getting really fast insights with the looking at the data, visualizing it, and also adding collaborative features. So you can have multiple scientists in the same room talk about some interesting feature that they're seeing in the data. A really big advantage of this, what we found, is actually leveraging the GPU to do high performance real-time visualization. So being able to quickly pull up a really dense data set, interact with it, change some of the visualization parameters, and gain insight that way. And we all know about the benefits of using XR over the traditional desktop tools. This was built for the Sea Level Change project. They were the initial sponsors of the development of this VR application. And with that, they also have this virtual Earth system laboratory where a lot of our data sets that we use for this demo are found. Here's a short video of what SciVR looks like, and this highlights the quick interactive, quick data interactions and being able to slice through the volumetric data. So this was a really big benefit that the scientists really liked. There's not really a good desktop application that does this nicely. There are tools for doing this, but you have to kind of drag the borders around, or they're kind of clunky compared to just using your hands and VR controllers to slice through the data. So this was a really nice benefit of this. I'm going to zoom a little bit or fast forward. So another nice thing is being able to quickly, change the visualization, change the color ramp that you're using, the scaling, so you can kind of bring out the details of what you're looking at. Here's another similar video. This is combining 2D data, so looking at the surface. And in this case, we're looking at ocean temperature anomaly. So it's hard to see where these large red blobs, how deep they extend beneath the ocean. So most of the time when I look at these maps, it's only from a 2D view looking at the surface. So we don't have a quick way of looking beneath the surface at different ocean depths. So VR has been helpful for quickly getting and then that answer. What does this look like beneath the surface? And it's kind of hard to see in this video without having a stereoscopic view, but kind of fast forward to looking at from a top-down view, so you can actually see these red blobs, which is near the equator is actually the El Nino anomaly, and we can see how far down it extends beneath the surface of the ocean, which actually isn't that much. Things kind of normalize pretty quickly the further you go into the depths of the ocean, which was an interesting thing that I found, being a non-scientist, just looking at the data. One more example here, just other various data sets. So this is looking at tropical cyclone, Typhoon Trami, in this case, from data that's actually coming from one of our CubeSats. And if I fast forward a little bit, this is looking at the Columbia Glacier in Alaska and being able to get data values using the laser pointer. We also developed an augmented reality version of SciVR. The main complaint from the scientists who use SciVR was really, oh, I get motion sickness from using VR. So AR doesn't really have that issue, and also eliminates the need to switch between the headset and desktop displays. That was one of the grievances from the scientists. The downside, however, is there's a lot less computing power, and one of the big benefits that we found from SciVR is that high performance computing and being able to leverage the GPU. So that was a pretty big downer with using these other headsets, such as the HoloLens 2. And I'm going to fast forward here. It takes a while to load the data, for one. That was one issue that we found. And it doesn't look nearly as good as the VR version, just due to the available hardware on the HoloLens 2. So this was kind of a quick prototype. We didn't go too much further to improve it beyond this. So the big question here is, how has this actually helped Earth scientists? So it's been a great tool for science communication. So looking at outreach and public engagement, we did a lot of demos at conferences and got really good responsiveness from the public, and they're really excited to see this data. But for the actual hard science, it's been a harder sell. We can get those quick insights from the sheer responsiveness of the application, be able to quickly see the 3D structures and taking those fast iterative slices, so our brain can, process everything better than just looking at a 2D view of it. And it's been useful for collaborative discussion. So, hey, look at this unusual pattern where my finger is pointing. But it's been a struggle for scientists to really pick this up. And in my opinion, the top issue is really getting these large geospatial data sets into the headset. So the scientists, they want to see their data set that's available publicly on the web, but these data sets can be tens of gigabytes large, and you actually have to download it, pre-process the data, start a whole bunch of software, and configure complex VR equipment, especially if you're dealing with something like the Vive. And like I was saying earlier, the onboard compute power are from a lot of the commercial VR headsets, the ones that are untethered from a computer, are generally insufficient. unless we pre-process the data, reduce it so that it can be visualized on these headsets. And talked about the the lack of powerful GPUs. And a lot of these scientists, they don't have the computers or the laptops with the necessary GPU to really get something like SciVR going and working smoothly. And there's also a lack of web services that can stream the data. So we don't want to say download this 10 gigabyte large file when we only care about a small part of it. It'll be really nice if it can just be streamed into a headset. Another issue is that Earth science data formats, they're not in things like OBJ, which there are a lot of tools that can just take an OBJ file, put it into a VR application. They're in scientific formats like NetCDF or HDF, which aren't really used outside of NASA in Earth science all that much. The general complaints about XR, the motion sickness, wearing a headset, I'm not particularly as concerned about those. I think those are industry-wide challenges that will gradually improve as the technology evolves. So how do we overcome the primary challenge? We've actually done a pretty good job developing tools and services for a 2D world. So I work with the NASA EOSIS, or the Earth Observing System Data and Information System. So there's a rich set of capabilities, almost too many tools out there to help you work with your data, to download the data, and so forth. And one of these tools is the Global Imagery Browse Services, GIBS, or Worldview, which lets us view huge amounts of NASA's Earth science data holdings. So this is a project in which I'm one of the leads on. And if you haven't seen it before, go check out Worldview. It's really an interactive web mapping application that lets you view tons and tons of NASA Earth science data. You can go back in time and see how the Earth looked at that particular day, and you can zoom in and out and get different resolutions of the data. And there's also a variety of GIS software, geographic information systems, software that can retrieve and visualize data sets via standards compliant web services and optimized formats such as cloud optimized geotiffs. So we've mostly solved this for the 2D world. And here's what Worldview looks like if you haven't seen it before. And what, oh, okay. Yeah, so just think a few more slides here. So developing, so what we want to do is develop 3D data pipelines and services, basically emulate what's in the 2D world. And we have standards for 3D visualization, so things like GeoTF, 3D Tiles, and i3s. And there's commercial off-the-shelf software such as ArcGIS Pro that can support 3D data and working with voxels. So currently, this has been my focus, is developing these 4D visualization pipelines, the fourth dimension being time in this case. And we've developed several prototypes for GIBS serving data, data set examples like you've seen in this right column from various satellite instruments. And we've developed support in SciVR for streaming 3D tiles. So we're able to basically do that as a proof of concept. However, there does remain several challenges of supporting heterogeneous data types. So things are very different if you're working on generating terrain meshes versus point clouds, and looking at things at centimeter scale versus kilometer scale from satellite observations. So yeah, happy to discuss these challenges and collaborate more across NASA and folks on the XR-TIM. So this is my last slide. With that, I'll be happy to take any questions.
All right, any questions around the loop? I do have one question. So have y'all considered running some of these applications on the cloud where all the rendering's done remotely and the visuals are streamed, similar to what's done on various video games? This might help requiring people to download the large amounts of data and also requiring them to have heavy-duty PCs locally. I'm just wondering kind of what your thoughts on that.
Yeah, that's exactly what we want to do. Basically build the services to stream the data. So there's a really complex data pipeline where we have the raw data that's coming from the satellite that has to be processed into these scientific data formats. And then we have to add another step to that pipeline to, to render it and be able to stream it nicely to VR applications, similar to how video games are being handled these days. So yeah, that's what we would love to do. And if others are doing it, we'll love to hear more.
Awesome. Also, I know there's ways to process all the data on desktops that have heavy-duty GPUs and just stream the visuals to a lighter weight HMD, maybe like the Oculus or some other lighter headset. Have y'all looked into that any?
Yes, somewhat. We've been more focused on trying to build the pipeline, say in the cloud or on the web. But yeah, a lot of what we've developed so far has just been built in using Unity.
Okay. Any other questions around the loop? All right.